Imagine we were explaining the concept of area to a kid. We show them a rectangle and tell them that the area of the rectangle is 2 by 4, so the area is 8. We then show them another rectangle and the kid exclaims, the area is 2 times 4, or 8. We have to tell them that they're wrong and that the area here is 3 times 5, or 15. We go over more examples and the kid recognizes a pattern. They notice for every shape that we show them, we are multiplying the base by the height. And so for the next few examples, they are able to get it easily. We then show the kid a triangle and the kid says the area is 3 by 2 or 6. We then tell them that they're wrong and that the area is actually 3 by 2 divided by 2 or 3. Up until this situation, the kid believed that he had found the general formula to find the area of any shape. And we know now that this isn't true. This was the general formula to find the area of any rectangle. However, we have formulas for many different shapes, but what if we had a formula for any shape that would work? We know that the area of a circle is pi r squared. We know the area of a triangle to be base times height divided by 2, but what is the general formula or method to find the area of any shape? This is essentially what integrals and integration is. It is a method to find the area under any curve, or to put it more broadly, find the area of any shape. Let's go over the ideas of integration and how we are able to do this. Going back to the previous ideas about infinity and being infinitely precise, we're going to use other shapes that we know how to find the area of to find the area of any shape. The most convenient for us to use is a rectangle, since we know the area of it is base times height. So let's say we wanted to find the area under this curve. What we can do is we could set up some rectangles that match the height of the curve at any specific point. Now here, if we were to add up the areas of these rectangles, which we could do pretty easily, we can get a rough estimation of what the area will be. However, we know this isn't very accurate. So let's try to get a bit more accurate. And the way we can do that is by decreasing the width of these rectangles so that we have more of them and so that we can more accurately adjust for the changes in height. You can see as I decrease the width of the rectangles and keep adding more of them, we get more and more closer to what the area of the curve is if we were to, say, add up all the area of each individual rectangle. You can start seeing where I'm heading with this. So what we're going to do is that we're going to decrease the width of each individual rectangle by an infinite amount. Again, like the ideas of limits, we're never going to make it decrease all the way to 0. Since if it was 0, the area, even if we had an infinite amount of rectangles, all of their areas would be 0. And so we're just adding up essentially 0. So they have to still be a finite amount greater than 0. However, they need to be infinitely small and close to 0 as possible. Now don't worry, we don't actually add up the area of each individual rectangles. We sort of use some sort of shortcut when we're doing integration that makes this much easier.